For example 4, we're going to use power reducing identities, but we also have to break this up. So we're going to have to treat this as cosine squared of x squared. Now again, this is even. So when it's even, I need to use power reducing formulas because I'm not going to be able to just take one out and save it and convert the rest. So in this situation, we want to use the power reducing formula. So I'm going to go ahead and write this as 1/2 1 plus cosine of 2x. Right? So this right here is the formula, but then I'm going to square that because it was cosine squared, right? So this is our cosine squared part. Now, I want to make sure you got to be super careful with this coefficient. This 1/2 is also being squared. Okay, so please be intentional about that part. It's so easy to make that mistake. I'm going to pull the 1/4 out, and now I have 1 plus cosine of 2x all squared. Now, because that's 1 plus cosine 2x times 1 plus cosine 2x, I end up with a double distribution situation. So I'm going to write that as 1/4, and then I'm going to integrate. I'm going to have 1 plus 2 cosine of 2x plus cosine squared of 2x. So now, unfortunately, this is another situation where you have to use a power reducing formula. That is not ideal. I do know how to integrate this and this by itself, so that part's not going to be a problem. But this guy right here has another power reducing formula. So I'm going to do 1/4, and I'm going to go ahead and do this, the integral of 1 dx plus, let me factor out this 2 to this guy, so then I'm going to have 1/2 the integral of cosine of 2x. And then I'm going to have the 1/4, oh, got to put the dx on there. And then I'm going to have the 1/4, and then here's my cosine squared of 2x. So let's go ahead and take the power reducing of that. So you're going to have 1/2, 1 plus cosine. Remember, the formula is cosine of 2 theta. So 2 theta is going to end up being 4x here. So you've got your 4x, cosine of 4x dx. Okay, so taking a look at that, I'm going to go ahead and distribute this 1/2 through. So actually, no, I'm going to go ahead and factor out the 1/2, but I do want to treat this 1 as separate. So let's take this into account. I'm going to have 1/4 x right here. That's the antiderivative. Now, taking a look at this, you're going to have a little bit of u sub here. So you're going to have 1/2 du equals dx. So you're going to have an extra 1/2 to go here. So you're going to end up with 1/4. So let's do plus 1/4. And then, of course, the antiderivative of cosine is sine. So you've got sine of 2x there. Now let's pay attention to this last integration piece. Okay, so I've got this that I'm working with. So I've got 1/8, and I'm going to do the antiderivative of 1 plus cosine of 4x dx. So if I want to separate this, right, I'm going to drop this, I'm going to drop this. I'm going to end up with 1/8 times the integral of 1 dx plus 1/8 times the integral of cosine 4x dx. So I'm going to have to u sub again. So in this case, u is 4x. So you end up with 1/4 du equals dx. So now you end up with an extra 1/4 here. I know it's a lot of pieces, y'all. You just have to break it up into steps. You have to break it up into individual integrals. It really does help overall. So you've got 1/4 x plus 1/4 sine of 2x, and then plus 1/8 x, that's kind of an interesting one, and then plus 1/32 sine of 4x plus c. Now I do want you to pay attention that you've got like terms here. So you've got 1/4 x and 1/8 x. So if you add those together, you get 3/8 x. So if you want to make sure that you get all your like terms combined, you get 3/8 x plus 1/4 sine of 2x plus 1 over 32 sine 4x plus c. Now keep in mind that if you were to take the derivative of this, you should end up with this, but identities are going to be involved. So it's really tricky for us to look at this and say, how does that work? Because you're still going to have to apply identities in order for that to fit.